Let's now solve this circuit that involves a series capacitor, resistor, and inductor with a series voltage source. So the switch has been in the left position for a long time, long enough for the capacitor to fully charge so that there'd be no more current going through it. And then at t equals 0, the switch comes over into this position, which, as I pointed out, then brings the capacitor, the resistor, and the inductor in series with this voltage source. So let's start first with determining the initial conditions for the, let's find all the initial conditions. First of all, for the capacitor. Now, with the switch in this position, we have this resistor capacitor series branch in parallel with this 1 kilo ohm resistor. And it's been in that position long enough for the capacitor to charge up to whatever voltage it's going to charge, so there would be no current flowing through that. Let's just draw this part of the circuit for t less than 0. We have then a 1 kilo ohm resistor there. We have the 100 ohm resistor there. And then the capacitor is going to be an open circuit. No current will be flowing through it. It will be charged up. And we're going to call this then V sub C. So if this is an open circuit, no current flowing through it, there will be no current flowing through the resistor either, so there will be no voltage drop across the resistor. And the capacitor then will charge up to whatever the voltage is across this resistor when all of the 5 milliamp current source is directing its current through that resistor. So V sub C at 0 minus then is going to equal 5 milliamps times 1 kilo ohm, which equals 5 volts. Now, the resistor, as we've already pointed out, has no current flowing through it, so V sub R at 0 minus will be 0 volts. And the inductor is just hanging unconnected to anything, so there'd be no current going through it, and there would be no voltage drop across it. So V sub L at 0 minus is also going to be equal to 0. And while we're at it, we might as well go ahead and just observe or write down our observation that because they're going to ultimately be in series with each other, I sub C of 0 minus equals 0, I sub L of 0 minus equals 0, and I sub R of 0 minus equals 0. Now, let's get the conditions at t equals 0 plus, so just the moment right after the switch closes. And we can do those down here. We know that V is 0 plus across the capacitor, the voltage across the capacitor at 0 plus is going to be exactly what it was at 0 minus, which is 5 volts. Now, the voltage across the resistor at 0 plus, the voltage across the inductor at 0 plus, won't necessarily be what they were right before the switch, because when the switch changes, voltage across the resistor and voltage across the inductor can and frequently does change instantaneously. So how are we going to go about getting it? Well, let's draw the circuit for that instant in time. We have the resistor, the capacitor, the inductor, and the voltage source. Now we see that the inductor and the resistor and capacitor are all in series. We also know that the current, let's come on down here, I sub C of 0 plus, I sub L of 0 plus, and I sub R of 0 plus. Of these currents, which of them are going to remain the same? Well, the current through the inductor is going to stay the same immediately after as it was before. And right before it switched it was 0, so right after it switches it will be 0. And because it is in series with these, we know then that I sub R will also be 0 right after it switches. And I sub C will be 0 right after it switches. Those other two are 0 because the inductor limits how quickly the current can change. Since the current right after in the inductor is going to be 0, the other two will be 0 also. So now we know that because the current through the resistor is 0 right after it switches, the voltage across the resistor, which is just I times R, will also be 0. Now we have to determine how can we find what the voltage across the inductor is right after the switching. To do that, we're going to write a voltage loop equation. And let's just start here. I guess we're working on this now. Minus to plus V sub L, plus to minus V sub R, and plus to minus V sub C. So, doing a KVL, let's see, this is plus to minus 12 volts like that. Starting here and going around in this direction, we'll have negative 12 plus V sub L plus V sub R plus V sub C must equal 0. Or V sub L then is going to equal, taking the 12 to the other side. Now subtracting V sub R from both sides, and we'll note that V sub R equals 0. So minus 0 minus V sub C at 0 plus, which was 5. So minus 5. We get then that V sub L at 0 plus is equal to 12 minus 5 is 7 volts. And while we're at it, we might as well go ahead and find the values of the voltages and currents as t goes to infinity. So coming on down here, as t approaches infinity, we will have V sub C at 0 plus, V sub R at 0 plus, or not at 0 plus, at infinity rather, I'm sorry. V sub R at infinity, V sub L at infinity, then I sub C of infinity, I sub L of infinity, I sub R of infinity, and let's see. So, after a long period of time, this capacitor will have charged to a new value until it can accept no more charge. So once again, the current through this loop will be 0. Anytime you've got a capacitor in series with other devices, the current through them ultimately will be 0. So we can say then that all of these are 0. And V sub C at infinity is just going to be the 12 volts. V sub R is going to be 0 because the current through the resistor is 0. And V sub L at infinity is going to also be 0 because the current through it will be constant. We know that the voltage across the inductor is equal to the derivative of the current because the current is constant and 0. But because it's constant, the derivative of the current will be 0 and the voltage across the inductor will be 0 at or as t goes to infinity. So we've now got our initial conditions, our final conditions. The next step for us then is to determine the dampening of this circuit. So let's just do the dampening up here. It's a series circuit. That means that alpha is equal to R over 2L, which is equal to R is, and we're using this resistor here. That's the one that's in the circuit after the switching. So that will be 100 ohms divided by 2 times 0.01. That gives us an alpha of 5,000. And while we're at it, let's just go ahead and get alpha squared then is equal to 2.5 times 10 to the 7th. And we also need to know what omega naught squared is. That's equal to 1 over L times C, which is equal to 1 divided by 0.01. And it's a 1 microfarad capacitor for C, so 1 times 10 to the minus 6th. And that then gives us omega naught squared is equal to 1 times 10 to the 8th. So we have then omega naught squared is greater than alpha squared, and the radical omega naught squared or alpha squared minus omega naught squared is going to be negative. So we can then calculate omega sub d, the damped frequency. Well, because the radical is negative, that tells us the circuit is underdamped, and we need then also to know what the damped frequency is. Omega sub d is equal to the square root of omega naught squared minus alpha squared, which in this case is equal to 1 times 10 to the 8th minus alpha squared, which is 2.5 times 10 to the 7th. And the square root of that then gives us omega sub d is equal to 8660. I'm going to go ahead and carry along a couple of decimal places just to help us identify this number as we're going forward. So omega sub d, the damped frequency, the frequency at which this thing will be oscillating as it dies out in its new value, will be 8660.25, and of course the units of omega are radians per second. With the initial and final conditions, and also knowing what alpha and omega sub d are, we're now ready to go ahead and write the solution. Because the circuit is underdamped, we know that the voltage across the capacitor, V sub c as a function of time, is going to equal the final value of the voltage plus e to the minus alpha t times b1 cosine of omega sub dt plus b2 sine of omega sub dt. Plugging in those values that we know, we get then that V final is 12 volts plus e to the minus alpha is 5,000 times t times b1 cosine of 8660.25 t plus b2 sine of 8660.25 t. Now, setting t equal to 0, we get then V sub c of 0 plus is equal to 12 plus e to the 0 is 1. The cosine of 0 is 1. The sine of 0 is 0. So we're left with then 12 plus b1 is equal to the initial voltage on the capacitor. We know the initial voltage on the capacitor is 5 volts, so we have 5 minus 12 gives us a b1 of negative 7. Alrighty, in this case we're able to solve for b1 independently, and we now need to just get b2. As we've done in the past, we'll get our second equation of b1 and b2 by taking the derivative of the voltage. So dv sub c dt, which we're going to be evaluating at t equals 0. But let's go ahead and first of all write the expression for dv dt. Of course, the derivative of the constant 12 is just 0, so there is no constant hanging out here. Then we have the derivative of the exponent times these sine terms, plus the derivative of these sine and cosine terms times e to the minus 5,000 t. So we're going to have then dv dt is equal to negative 5,000 e to the minus 5,000 t times b1 cosine of 8660.25 t plus b2 sine of 8660.25 t. Then we have added to that the derivative of this times the e to the minus 5,000 t. So the derivative of this first part is going to be, derivative of the cosine is negative sine, so we're going to have a negative out in front. We're going to have a b1 there. The chain rule kicks out a 8660.25. Then again, the derivative of the cosine is the sine of 8660.25. It has the derivative of the first term. plus the derivative of the second term. The derivative of the sine is the positive cosine, so it'll be plus B2 times, chain rule kicks out the 8660.25 again, times the cosine of 8660.25t. Close that parentheses, and we've got still have that exponential term. I'm running out of room here, so let me just write it down here. The derivative times the e to the minus 5000 t, all multiplying this thing here. Now we evaluate this at t equals 0, or we get then dv sub c dt evaluated at t equals 0. We're going to have a minus 5000 e to the 0, that's just 1, times b1, the cosine of 0 is 1, so I'll get a b1 term here. The sine of 0 is 0, so that closes off that part. Plus, now this term right here has the sine, and that's the sine of 8660.25 t. I left the t off of there. When you evaluate this sine term at t equals 0, that goes to 0. Here we've got b2 times the cosine of 0. The cosine of 0 is 1 times e to the 0 is 1. So we're going to have plus 8660.25 times b2 is going to equal dv sub c dt evaluated at t equals 0, which from previous experience we know has got to equal I sub c at 0 plus divided by c. Now we'll recall from the previous page that the current through the capacitor right after it switched was 0 because it is in series with the inductor. Therefore, this term right here, the negative 5000 B1 plus the 8660.25 B2 must equal 0. Now we've got B1 equaling 7. When we plug B1 equals 7 into here and solve for B2, we get then that B2 is equal to a negative 4.04. And the units on B are volts. So we have now then our final solution. V sub c as a function of time is then equal to, coming up here to this, we have the final value 12 plus e to the minus 5000 t times b1, which we found to be a negative 7, cosine of 8660.25 t, and then b2 turned out to be negative also, minus b2, which was 4.04 times the sine of 8660.25 t. And hopefully you can read that. But that gives us our final solution. Now we can go through and we can determine, or we should go through and determine that it meets both our initial and final conditions. The initial condition, the voltage on the capacitor has got to be equal to 5 volts. Do we get that? Well, at t equals 0, this term here will be 1. This cosine term will be 1, multiplying a minus 7. And the sine term over here will be 0. So we'll have 12 minus 7. Sure enough, we get that the initial voltage is 5 volts. And the final voltage is pretty obvious. We've got this exponential term that will be dying out as omega goes to, or as t goes to infinity. So we'll have then that V sub c, as it heads toward infinity, will equal the 12 volts. I've drawn here the graph of what this function V sub c of t is going to look like. It starts out at t equals 0 at 5 volts. It ends up at 12 volts. And because it's underdamped, there is some oscillation. And it's hard to see it here, but the natural frequency of this, or not the natural frequency, the damped frequency of this oscillation then would be 8660.25 radians per second.